This topic, that is, we talk about multi-class SVMs. So we know that SVM, that is a binary classifier. That means we can only use SVM to tell which class it belongs to, either class 1 or 2. That is indicated by +1 or -1. Yeah. So how do we turn the binary SVM classifier into multi-class SVM? That is this topic. Yeah. So we are going to use SVM as a building block and then combine this building block to form a multi-class classifier. Yeah. Now, before we go into detail, we are talking about the multi-class classification problem. Now we still have a data set. Yeah, so each data set, the data set we have different samples, x1, and then so we are going to label that because now we're talking about multi-class classification problem. So x1 may belong to C1, that is the class 1, x2 to C2, the class that is 2, C and the class may be 3, so and so, depending on the applications. So now that is more than 2 classes. So in order to combine SVM to form multi-class SVM, we have a number of approaches right here. These are not all approaches, but some commonly used approach. The first one we call this is 1 against 1. The second one, 1 against or binary decision tree and binary coded. And then we are going to look into the details one by one. Okay. So when we talk about 1 against 1, we need to require that if we talk about the R class problem, for example, R that is 5, it means that we have 5 classes. And then when you substitute that into this equation, that is the number of binary classes. This is the number of the binary class SVM classifiers required to form this 1 against 1 SVM. Yeah. Okay. So I leave the details right here. So this is just an example. And now in the next page, and then so this slide just give you graphically what I just mentioned. What I'm going to mention, that is about now we have 3 classes. Class A, class B, class C. So R, that is 3. So if we are going to apply this formula, and then so we will come up with this one, which require 3 classifiers. Now, why this is called 1 against 1? Because we are going to design the classifier like this. When we use A, the class A, and then we have class B, we are going to design one hyperplane. That is the blue line right here, which is going to tell whether the input class, that is A or B. So to train this WTX plus W0, we have to relabel AB. Yeah, because now from the blue hyperplane here, which is going to assign A to be +1, for example, B to be -1. So that means in the beginning, we have class A, class B, class C. So when we design this hyperplane, we have to reassign the label. For A, that is +1, B, that is -1. So we come up with the hyperplane right here. Now we have the green. Yeah. So for example, we are going to do another combination, that is A versus C. We have another hyperplane, that is another set of Wx plus W0. Okay, so in this case, we can assign, for example, +1, -1. So that means this hyperplane can only tell you that whether it is either A or C using +1 and -1. So the same concept apply to B and C. Yeah, so we have B, C, another hyperplane, WTX plus W0. Now, although I use the same symbol W, but actually they will have different numerical value, because when we use different data set, for example, this is +1, -1, so we have the data set B and C to train W and W0. Yeah. And now once we have these three hyperplanes, yeah, so that is 1 against 1. Each one we only have A against B, A against C, B against C. So 1 against 1. Now once we construct this hyperplane, and then that is how it works in practical. For example, we are going to have a new point right here. We would like to know which class it belongs to. Substitute this into each of the hyperplane. The blue just tell you that it belongs to A. Yeah? Okay. When you substitute this point into this B versus C hyperplane, it just tell you that it is B. Yeah? So now when we use the green hyperplane, it just tell you that it is A. So using the majority routing, we have 2A and 1B. So the majority routing just tell you that this point is A. Yeah. So you can test any point anywhere in this workspace or the feature space, but when you talk about a point right here, we just find out that something strange happened. The blue line just tell you that it is B. The green line just tell you that it is A. The red line just tell you that it is C. Yeah. So when you apply the majority routing, we do not come up with the final decision. That means we need to use another method to handle this case. Yeah. Say using the value right here. But anyway, now when we have this 1 against 1 approach, we know that we have 3 SVM. SVM 1, that is for A versus B. And then SVM 2, that is for example, A versus C. And then the third SVM, that is B versus C. They will accept the same sample X. So this is after you trained the network, after you trained the SVM, and then in order to detect a point which class it belongs to, and then so we come up with this structure. Collect the output, this block which is going to apply the majority voting to tell you which class X belongs to. Yeah. Okay. So input, that is multiple input because X it is in a two-dimensional space. The output, that is, which just tell you that whether it belongs to class A, B, or C. Yeah. Now we are going to talk about 1 against all approach, and then so this is the, if we have R classes, we will have R. We need to have R SVM. Yeah. So this scenario is something like that. An example, that is 3 classes as well. When we talk about 1 against all, that means, say, we have the class A, and then so we are going to design an SVM which against all the rest class A, and then we decide that is +1, and then B and C, we group it together to form the data set. Yeah, so B and C, we label that, and then they have the same label, -1. So design the hyperplane. This hyperplane can tell you whether this is A or not A. So -1, that is not A, but we do not know whether it is B or C. Yeah. So the same. So when we talk about B versus A and C, construct a linear supporter machine, and then this one I just assign the label +1, this side -1. So we have to relabel the class AC to -1, B to +1, and then the same for C. We have A, B right here. So this one -1, this is +1. After relabeling, decide the hyperplane. Now let's see how, when we put them together, how do we test a point? Say we have a point right here. a new X. Using this hyperplane, the red just tell you that this is not B. And then so now the green just tell you that it is not C. And then the blue just tell you that it is A. Yeah. So this is A, not B. When it is not B, it is just either A or C. Yeah. So when it is not C, it means that it is either A or B. Apply the majority voting. We have 1A, 1A, another A, 3A, and then 1B right here, 1C. So majority voting. So it just suggests that this is A. So the same issue happens when we have a point right here. You will just find out that we cannot make a decision. Yeah. So we can have some other alternative to deal with this case. Now the same, we have 3 SVM. SVM 1, that is for A, and log A, that is B, C. And then SVM 2, so we have B versus A, C. And then SVM 3, that is C versus A, B. After we trained these 3 SVM, we put a new sample into this SVM, these 3 SVM. That is, for example, this one. Collect the output. Each output will give you +1 or -1 according to the information of each case. Apply the majority voting right here, which will give you whether this is A, B, or C. Okay, to deal with the undefined region, in some literature, they just take the average. For example, the red and blue come up with this line, and then the green and blue come up with this line, and then red and green, which give you this. So we come up with a new hyperplane in the star shape, which can cover the whole region. And now the next method, that is the binary decision tree. The binary decision tree, that is, we label the dataset. For example, if we have R cases, we require to have R minus 1 SVM. The reason why, just take a look at this case. Now, this is the problem we have. We have 7 cases, so the first SVM just checked all possible X. This is X. When this X get into the SVM, this is the hyperplane right here. It just tells you that whether X belongs to 1, 5, 6. For example, this is +1. This is -1. So that means we just separate the dataset into 2 cases from the main classifier SVM right here. So all 1, 5, 6, that is, we assign the label to be 2 + 1 instead of class 1, 5, 6, and then the rest to be -1. So when a new X gets in, and then it just tells you that whether it is 1, 5, 6 or it is 2, 3, 4, 7, it will not tell you that it belongs to 1, 5, or 6. It just tells you that it could be 1, it could be 5, it could be 6. Yeah. Now, when we get to this point, we are going to, based on 1, 5, 6, we are going to design another classifier. This classifier, that is the second layer, which can tell you that whether it is 6. For example, we relabel one size 6 to +1 represents 6, 1, 5, -1. So based on this new labels as well as this data set, we change the SVM. This SVM just can differentiate 1, 5, 6. Okay, so we repeat this process. We come up with a layer, a tree diagram. So this is why we call this is the binary decision tree. Yeah. So the advantage of this SVM, that is, the design is very simple. Yeah, so we can just simply draw a line right here to divide the data set into half, and then so one half, that is +1, another half, that is -1, and then when we consider the half of the data set and then do the separation until we reach the final class. For example, if it is +1, x is classified as 156, and then that is +1. Use this SVM to tell you that whether it is 1, 5 or 6. If this SVM give you -1, we just use this classifier using the same x right here, and then to tell you that whether the class, that is 1 or 5. So that means we will have, this is the block diagram, when you have x right here according to this -1 or +1, to use the same information to determine the next layer's output, that is -1 or +1. So the disadvantage, that is the error, will propagate if you make the wrong decision in the first branch, and then you do not have any way to go back to the correct branch. The next one, that is the binary coded approach. So assume that we have R classes, and then this is, we require log 2 R SVM. This symbol, this operator, that is the ceiling operator. That means we are going to round up this number. Yeah, round up this number. So consider that we have 7 classes, and then that means R, that is 7. Substitute that into this equation. This expression will give you 3. Yeah, so we require 3 SVMs to construct this multiclass SVM classifiers. And now take a look at this one. This table, we are going to assign the code to represent the class. For example, because according to this expression, we know that we require 3 SVMs. So 7 classes. So the first class, I'm going to use SVM1 to be +1, +1, +1 for 2 and 3. And then 2, that is +1, +1, -1. So just consider all the combinations. Yeah. So each combination, that is unique combinations. So that means we are going to do something like that. SVM1, SVM2, SVM3. After we do the training, feed in X into these 3 SVM, because each SVM will give you either +1 or -1. So according to this table, and then according to this table, and with the output of this SVM, and then say this is +1, the output is +1, +1, +1, which according to this table, it just tells you that this X belongs to class 1. Yeah. Now, because this table, that is what we assign, that we assigned this code to class 1. So once we have this table, let's take a look. How do we design SVM1? So SVM1, that means which will generate +1 if the input data belongs to 1, 2, 3, 4. And then it will give you output -1 if the input, that is 5, 6, 7. So to train SVM1, we are going to group the data set class 1, 2, 3, 4 to be one group with the label +1, and then another group 5, 6, 7 give the label -1. That means relabeling, that is required. So the same applies to SVM2. SVM2, these two, so we have 1, 2, 5, 6. We assign +1 to be the label. 3, 4, 7 to be -1. So we label the dataset. Use the relabel the dataset to train SVM, so the SVM2 can differentiate whether the input X is either 1256 or 347. Yeah, so each SVM cannot tell you which class it belongs to, but when you combine them together using this table lookup, it will map to an individual class right here. And now the problem is that when we consider 7 classes, we do not have -1, -1, -1, but there is possible that the X will lead to this combination. In that case, that is an undefined case. Yeah. Okay. And now a very brief conclusion. This topic that is about support vectors machine. Yeah. So we have the linear supporter machine. We can also implement that as the hard and soft classifier. Hard classifier, it means that we are talking about the hard and soft margin. Yeah, so the hard and soft margin, that is, for the hard margin, we do not accept error. For the soft margin, we are going to accept error during the design of the SVM. So in order to turn the linear SVM into the nonlinear one, we can use the kernel function. The kernel function, that is to map the feature space from the original feature space to a high dimensional feature space. In the high dimensional feature space, it is possible that the data, the data set will be linearly separable, and then so we turned the non-separable classification problem using linear supporter machine to a linearly separable case when the data set is in the high dimensional space. Yeah, so you will just find out that the support machine, that is very effective tools, because we use the optimization theory to design the support vectors, to design the gains, or to design the weight of the support vector machine. And also support vector machine, that is a binary class classifiers. If you would like to deal with multi-class classification problem, we have to use support vector machine as a building block and then combine them together to form multi-class classifiers.